Let's take a look at reliability in cloud systems design. Like this video and subscribe to the channel for more great cloud tips. Reliability is concerned with keeping systems operational when things go wrong. Reliability is the ability of a system to keep doing its job correctly despite failures. The key word there is despite. Failure is a reality assumed rather than avoided. Disks fail, instances stop, networks partition, and an availability zone occasionally loses power. A reliable design does not try to prevent those events, since you often cannot. It arranges things so no single one of them takes the whole system down. Reliability is where an architecture either earns trust or quietly loses it. For a simple system, the goal is avoiding avoidable downtime. One server dying at 2 in the morning. For a complex system with dozens of components, the risk changes shape entirely. Every dependency you add is another thing that can fail, and their failures combine in ways nobody planned. Why design for this up front? Designing for reliability up front is far cheaper than retrofitting it after an outage. The retrofit changes how data is stored and how requests are retried. That touches everything. Learn more at systemsarchitect.io. Like and subscribe to the channel and playlist. Redundancy is the first tool you reach for, and it means having more than one of anything that matters. The goal is eliminating single points of failure. That is any component whose loss stops the entire system. 2 web servers behind a load balancer survive the loss of either one. 1 web server behind a load balancer survives nothing. In AWS terms, that means spreading instances across at least 2 availability zones. Those are physically separate data centers. Managed services follow the same pattern. An Amazon RDS deployment in multi-AZ mode keeps a standby copy in another zone and fails over automatically. Trace each request path and ask what breaks if any one box disappears. Redundancy protects you from hardware and infrastructure failure, but it happily replicates a mistake. If someone drops the wrong table, every replica drops it at the same moment. That is what backups are for. They cover a completely different class of failure. Accidental deletion, a bad migration, corrupted data, and ransomware all need a point in time you can return to. S3 versioning, RDS automated snapshots, and DynamoDB point-in-time recovery each provide that rewind. What good is a backup nobody has tried? A backup you have never restored is a hypothesis, not a safeguard. So restore drills belong on the calendar. Keep at least 1 copy in a separate account or region. Reliability becomes a design input only when you attach numbers to it. Recovery time objective, or RTO, is how long the system may stay down. Recovery point objective, or RPO, is how much recent data you can afford to lose. An internal reporting tool might tolerate hours of downtime and a day of data loss. A payment system needs minutes and seconds. Those 2 numbers drive the whole recovery strategy. And the cost. Nightly snapshots are cheap. Continuous cross-region replication is not. Agree the numbers with the business first, then buy exactly the architecture they require. Availability is the headline reliability number, and it is quoted as a percentage of nines. What does 2 nines actually allow? 2 nines, or 99%, allows about 3.5 days of downtime a year. 3 nines, or 99.9%, allows roughly 8 hours and 45 minutes a year. That is about 43 minutes a month. 4 nines, or 99.99%, allows about 52 minutes a year. 5 nines, or 99.999%, allows about 5 minutes a year. Availability is not the only measurement. Mean time between failures tracks how often things break. Mean time to recovery tracks how fast you get back up. Recovery is usually the more useful lever. You can rarely stop failures, but you can almost always shorten them. Those numbers roll up into an SLI you measure, an SLO you commit to, and an SLA you promise. The gap between your objective and 100% is your error budget. Redundancy only helps if something notices the failure and routes around it. That job belongs to health checks. They probe each instance on a short interval and mark it unhealthy after a few consecutive failures. A load balancer stops sending traffic to an unhealthy target within seconds. An autoscaling group goes further. It terminates the failed instance and launches a replacement from the same template. That combination is self-healing. It handles the most common failure in cloud systems without anyone waking up. Health checks need care, though. A check that only confirms the process is listening will pass while the application is deeply broken. A deeper check catches far more but can mark the whole fleet unhealthy over a brief database hiccup. Not every failure has to be all or nothing, and the best systems fail in pieces rather than at once. Graceful degradation means shedding non-essential functionality so the core keeps working. If the recommendations service is down, an online store can still show products and take orders, just without the suggestions row. Circuit breakers make this practical. They cut off calls to a dependency once its failures cross a threshold. That prevents a slow dependency from tying up every thread in the caller, which is how one failing service takes down 5 healthy ones. Set aggressive timeouts too. Add retries with exponential backoff and jitter. Retries without backoff turn a small blip into an outage of your own making. Reliability gets dramatically easier when your compute layer holds nothing you cannot lose. A stateless application server can be terminated and replaced at any moment. Every replacement is equivalent to the one it replaced. Move session data to a shared store, such as Amazon Elasticache or DynamoDB. Move uploads to object storage like S3. Once state lives outside the instance, failover becomes routine. The stateful parts do not disappear. They concentrate into databases and queues, which is what makes reliability affordable. You buy expensive replication and failover only where it is required. An untested reliability mechanism is an assumption, and assumptions fail at the worst possible time. Chaos engineering means deliberately injecting failures to see whether a system behaves as designed. Start small. Terminate one instance during business hours and watch whether traffic shifts without a user noticing. Then escalate, fail over a database, block a dependency, or remove an entire availability zone. Game days run a realistic incident end to end. They expose the human half of reliability. Where do real incidents actually go wrong? That half is usually where the real gaps are, in an out-of-date runbook or an alert that goes to someone who left. The obvious benefit is availability, since users experience a system that keeps working through events they never learn about. Operations improve sharply. Failures that once meant a pager at 3 in the morning are absorbed automatically. Reliability also protects revenue directly. Downtime in a transactional system is orders you never recover. The same investments improve your ability to deploy. A system that survives an instance disappearing survives a rolling deployment too. Reliability is not free, and every 9 you add costs meaningfully more than the last one. A prototype or an internal tool does not justify a multi-region failover. A single zone deployment with solid automated backups is the honest answer. Multi-region active-active designs bring hard problems around data consistency and cost. Reach for them only when the business cannot tolerate a regional outage. Over-engineering carries its own reliability risk. A complicated failover mechanism is one more thing that can fail. Choose the simplest design that meets your RTO and RPO and spend the savings on testing it. Reliability is keeping a system operational despite the failures you know will happen, using redundancy for infrastructure loss and backups for everything else. It matters in simple systems to avoid ordinary downtime. It becomes critical in complex ones where many components fail in combination. Design it by removing single points of failure, agreeing RTO and RPO, automating detection and replacement, and regularly testing that all of it works. Thanks for checking this out. Hope you learned something. Find a lot more articles and guides on both systemsarchitect.io and codeguides.io.